Gentlemen, introduce yourselves.
I'm Levi.
Ryan. Rob.
What we got going on? We're doing the brick one.
Yeah.
What have you done so far with this one?
We calculated our initial, from those steam tables, the initial steam table and the quality, the initial pressure and the initial volume.
I guess, let's do this. Just tell me in words what's happening in this problem.
System heats up, the cylinder raises up to hit the other brick.
Okay, sure. So there'd be some like flame or something like that heating it up.
Mm-hmm. Yeah.
Okay, sure. So it heats up, lifts off that lower brick.
Yeah. So it touches the higher brick.
Gotcha. Okay, so there's a lot going on in this problem.
Yeah.
So where did you start with it?
We start with it on the when it's resting. There's some given values for your quality and your temperature.
Speak almost like shouting. So
right. Yeah, quality, temperature, and a little bit of the mass of the water.
Okay, sure.
So using those, you can look at the steam table and find your values for your
Specific volumes of the fluid and the gas, and then we use the quality equation to find the.
One thing, when I look at these problems, one thing I always try to look for are two different things in each state. For example, at state 1, I know the temperature and I know the quality. Where does that put you on a two-phase, in a PV diagram, for example?
You're underneath the curve.
You're underneath it. So if I drew, what should we do, PV? So if I did PV, something like that. So you're saying you're somewhere underneath that envelope, probably halfway between the two. Okay, sure. So we know temperature, and if I know temperature, an isotherm on a PV diagram looks something like this. It comes straight across, and it comes down.
Right.
And if I know temperature of 120, that allows me to find the initial pressure at that state. And it turns out that I can find anything I want to with knowledge of two things. Yeah, speak almost shouting.
So yeah, you got your relationship between pressure, temperature, and volume.
Okay.
And you can start to decompose those to find your secondary values for that second stage. We're increasing the temperature, so you're going to have some change in temperature. But does that affect you on the isocline? Like, you're just traveling across that, or you're raising it a little bit? Because the temperature increase is only 20 degrees Celsius. Or 25 degrees Celsius.
Oh, yeah, okay. So we'll go from 120 degrees C up to 145.
Right. So along that diagram, you're still staying on that horizontal path.
Okay, sure.
Increase. You're not crossing into another.
Okay. So we're still talking about the point before the brick lifts off. Is that right?
Right.
Yeah.
Okay. So before the brick lifts off, think about, now we're looking for, in the second step, we know everything about the first step. The second step, we know the temperature is 145 C. We need something else, though, to figure out where you are.
Table to find, from that 145 degrees Celsius, to find pressure that was related to that temperature.
Okay, sure.
So then we've got two items.
So if you went to the saturated liquid table, you figure out what line you're on at 145.
Yep.
That assumes, though, that you're still in the two-phase envelope.
But we don't know that.
You don't know that.
Yeah.
So if I
We're
move...
not given the quality.
Yeah, so in a PV diagram...
quality is going to change with temperature.
Yeah. Typically on a log scale, you're going to be pushing to the right. Quality will change with temperature. Where am I going on the PV diagram? If that's state 1, I can call this state 1.
To the right.
Okay, so we could go to the right?
You are increasing pressure, so...
Yeah, I would agree.
Okay. You could be going left as well.
Maybe going left? Sure. So both of those ideas would suggest that the volume is changing. Volume's either getting bigger or smaller. And this is before the brick is lifted off?
We know we haven't changed the mass.
Mass hasn't changed, right.
Specific volume at that temperature, 145 degrees. Can we find the volume? We know that also that if the plate hasn't lifted up yet, that the volume hasn't changed.
Oh, okay.
Right?
Yeah, the plate hasn't changed. The volume...
Before the pressure is going to keep going up. So that instantaneous moment, it's got the same volume.
Okay, sure. So if the volume is the same...
The pressure is going to... So you're going up.
Yeah, for sure.
Okay, cool. Okay.
Going up, your volume stays.
All right, sure. So in a PV diagram, yeah, you're right. We can only go up or down. We can move up or down on this thing. You propose we're going up. Why?
Because your pressure is increasing.
Why is...
Your temp's going up, so your pressure's got to go up.
Sure.
Line's not changing.
Yeah. Let's draw a higher isotherm here. Temperature is going up. So I would agree with you. We go up. who's to say, though, that we're still in the two-phase region? What prevents it from going up into here, into a superheated region? This is where it gets challenging if I don't know enough. So let's call this state 1. So we've called state 1, T1 is equal to 120, quality 1 is 0.5. Let's do, so we know T2 is equal to 145 degrees C.
Temperature and quality, like a linear relationship or something that we can solve for the quality using just the change in temperatures.
Possibly, we could do that. Assuming that it was still in the two-phase region, we might be able to come up with quality.
That would require us to be inside the region.
Yeah, we don't know for sure. We have to get a second intensive variable in the second state. The question is, what else do you know?
Now, can you jump to the third stage and use some of that and work backwards? Because now we have triple the volume of the initial volume in the third stage.
Yeah, in the third stage, the volume will be 3 times as big. But the second stage, we can get there without having to jump to the third stage. And there's one other thing that we can find.
We can't use gas equations because there's still some liquid in there.
Yeah, we can't. Stay away from ideal gas. What you said is there may or may not be liquid remaining once it hits 145.
You can't determine that directly from the steam table.
We can. We'll end up doing it. We will be able to find it in the steam table. But to locate anything on the steam tables, you need to know 2 things. 2 intensive variables. What's the specific volume in state 1?
0.8.
That's the total volume.
That's the total volume.
So divide that by 2.
Is 0.4466.
Yeah.
Okay. So you do have the specific volume at state 1, whatever it might be. What's the specific volume at state 2? V2 is a big question mark. How much mass is in there in state 2?
Still
Same as before, 2 kilograms.
Still 2 kilograms with you. Yeah. What's the volume in state 2?
Same.
Yeah.
Yeah.
The volume divided by the...
Right. So here's the trick. V2 is equal to the actual volume at 2 divided by the mass. The mass stays the same. The volume at 2 is the same as the volume at 1. And that says, so V2 is equal to V1, mass is the same. That means that specific volume
is the same in both.
Yeah, right. So if you know the specific volume in state 1 by looking in the saturated water tables, now you know the second thing in state 2.
So you've got a temperature and a saturated volume.
So you've got
give us our pressure.
So you ought to be able to find it. We need to figure out where we are in that two-phase region. The way I always start these things is to start with the saturated water table. And the 2 things we know the temperature in state 2 is 145, and you know the specific volume in state 2. What I would do, let's look at the saturated water, the temperature table, and I'm going to keep coming down. The temperature is on the left, and I'm looking for 145. I see that right at the bottom, and this column gives me the specific volume of the fluid and the vapor. So the vapor, here's the specific volume of the vapor on the right, and I come back down to 145. Specific volume of the vapor is about 0.45 cubic meters per kilogram. What did you calculate for the specific volume at 2?
We dumped it into yeast and I'll put the same number, 0.4466.
So you got a value that was right at the saturated vapor. What does that tell you about the quality?
It's 50%.
Yeah, it's still somewhere
in that close range. Yeah.
What number did you get for specific volume, the exact number?
0.4466.
Okay, so you got a value 0.4466. That's actually a little bit bigger than the specific volume of the vapor.
The vapor would only decrease if the volume was. The volume would only decrease in the mass.
When I look at that, when I look at your number compared to the saturated water tables, if the specific volume is large, it means the density is really small. And if we're at a specific volume that's greater than the specific volume of the vapor, that means the density is less than the density of saturated vapor. So if the specific volume is greater than the specific volume of the saturated vapor, it says that the density is less than the density of saturated vapor.
Overall density.
Yeah, the question is now, how can you use that to figure out where you are on this table?
Well, density is a larger volume. Density is the inverse of specific volume.
Yeah, density, the inverse of specific volume.
Less dense is a larger volume.
Less dense is a larger volume. In terms of figuring out where we are on the table, what if, for example, let's say we're at 20 degrees C for whatever reason. Here, this is a liquid, saying there's 1 kilogram of water occupies only 0.001 cubic meters. Here's the saturated vapor. It occupies 57.762
That would
cubic.
be a ratio you can find the quality.
Sure, we could use that to find the quality, assuming that we're between this small value and this high value. In this case, if we were around 30, 29 or 30 or whatever, we would be a quality halfway from the fluid to the vapor, and that would be a quality of about 0.5. But now you're in a situation where you found a specific volume that's slightly greater than this. So you're off to the right. If you use the quality equation, you would get a quality of, let's say, 105%. What is it? That's meaningless, right? A quality of 105%. What that means is that you're now outside of the two-phase envelope. You're no longer on this saturated water, this temperature table. So now where do we go? We're no longer on this table.
You have to move to the next table.
Yeah.
Superheated fluid.
All right, let's go to so we go to the superheated vapor table. So here, now what I've got, so we're off the saturated water table. Let's say in a different example maybe, you now know that your pressure, let's say for example the pressure is 0.05 megapascal for some different problem or whatever. And now we know the specific volume. That locates us on this diagram. This is 0.05 megapascal, specific volume of 4.8 cubic meters per kilogram. Puts us on this line. I could use that now to calculate the temperature under those conditions. Yeah, so we can get the exact temperature. One thing you found, though, is that in state 2, you agreed with me that we can only move vertically on the PV diagram. And it looks like you moved upward. The specific volume that you found was the specific volume of the vapor, and it was right in this region. I would say you moved up, all the way up.
Pass through that region.
Yeah, right. Just right past this region. So in state 2, I would put you, it sounds like you're putting yourself sort of right in this region for state 2. Yeah, so as you
heat, more pressure, more pressure, less volume.
Right. So when you work your way through these problems, you're always looking at each state, you're always looking for two different things, two different intensive variables. And in state 2, we happen to know that the temperature and the specific volume.
So we were thinking regular volume, not specific volume. Mm-hmm. That's why it's going down. Yeah, specific volume is going down because you're getting.
I would say that specific volume is remaining the same between states 1 and 2. Is that what you're saying?
I just meant throughout the problem, like when you get to the end.
Okay, sure. Yeah.
The next step, it gets
cool.
Smaller and smaller because now you've gone past the point of having any fluid, and you're at the point of having that gas just getting hotter and hotter and hotter.
Okay, sure. So the idea that the specific volume gets smaller over time.
Yeah.
I think you're thinking about the density. I would agree that the density gets smaller. What happens to the actual volume versus time?
The actual volume, it expands.
Yeah, the actual volume gets bigger, right?
Yeah.
So when you think about specific volume and you think about actual volume, just consider them to be one and the same because the mass in the system is the same. So I would say over time, the specific volume actually gets bigger. I agree with you, the density would get smaller, but the specific volume itself gets bigger.
They'd have to be their inverses, yeah.
Yeah, right. So what is so now we know everything about state 2. So you've solved that part of it. The dot is just to the right, in the two-phase envelope. What happens in state 3 now?
Well, it's triple.
Yeah, so in state 3, in state 2, the brick just lifted off the stops, right?
Mm-hmm. And now you're going from the bottom all the way to
Yeah, okay.
just before.
Sure. So what's happening between states 2 and state 3?
All the heat is going to
the expansion of the vapor.
Okay, sure. The vapor's
right?
expanding.
It's no longer going into the phase change.
Yeah.
Right.
So I think we're in agreement that brick is moving up between states 2 and 3.
Yeah. So then specific volume would triple then as well.
Okay, so in state 3, it sounds like you've got enough information you can find the specific volume at state 3. What did you say? It's 3 times?
Mm-hmm. Because the volume is 3 times larger and volume is directly proportional to specific volume.
Okay, so in state 3 then, if we know V2, that means we now know the specific volume in state 3.
Right.
So you got to search for something else, some other intensive variable at state 3.
If we had the specific volume, can we find the temperature?
If you had the specific volume, you could find the temperature, provided it was in the two-phase region.
It's not.
Yeah, and it's not in the two-phase region. All of that, by the time the brick moves, all of that liquid has evaporated. So we've got one thing, but we need to find another thing. Think about this. On the PV diagram, where do you go from state 2 to state 3?
Your pressure's increasing, so you're going to the left. But specific volume,
But your volume's decreasing.
yeah, you're going up from there.
Okay, we're going to the upper right, maybe?
Yeah,
Okay, sure.
It's superheated vapor.
Okay.
Whatever that is.
So we could go to the upper right, but I think it sounds like you're in agreement that we're moving to the right somehow because the specific volume's getting bigger.
Mm-hmm.
Okay, all right. So we're moving to the right somehow. And right when the brick leaves the stops, how does the pressure of the
Pressure would stay constant.
you think
because
pressure?
the volume is increasing.
Okay.
Yeah, it's going to lift the bricks in accordance
Sure.
to how much force is pushing down.
There you go. Yeah. So
pushing down.
right, yeah. So we have one brick per unit area to begin with. We still have one brick per unit area. And you're right. We move to the right, and we do so at constant pressure.
Yeah.
Cool. So now we know P3 is what, equal to P2? And do you know P2?
Oh, we can because it's now vapor.
Yeah.
So we can use the ideal gas law.
No, careful.
No.
I cut you off right away. Don't ever use, with steam, don't ever use ideal gas law. Yep, stay away from that. I would always use the table or ease to do this.
So we can just use that ease command.
Yeah, you could do it in ease. You can find it in the table as well. What are the two things we know at state 2? We know the temperature.
Specific volume.
You know temperature and specific volume. You can use those two pieces of information to figure out. Yep. Okay. So with those two pieces of information, we can find P2. With knowledge of P2, that means we know P3. So where you've gone with this, now we've found 3 different states. Maybe let's leave it at that, but in general, as you work through this problem, keep looking for these 2 different intensive variables so you can figure out where you're located on the PV diagram and in the tables.
And we just keep moving.
Yeah.
Stage for stage. Yeah.
Sweet. Well, thanks. Thanks, guys.
Thank you.
Thank you.